if we had a pendulum in like a box that isn't moving or accelerating versus a pendulum inside of an elevator that's accelerating up with an acceleration a, if we were to give these guys like the same initial displacement or whatever, get them oscillating, would their periods be the same? Would the acceleration that the pendulum, the additional acceleration, I guess, right? Because I guess there's acceleration while you're swinging, but would the elevator make a difference on the period? That is the question I'm going to try to answer with you guys. This is a question that came up on this thing, this colon questionnaire, this pendulum MCQ thing, and I want to show you guys how I would approach this. So for, we know that like for the period of a pendulum, it's equal to 2 pi times the square root L over G, right? So at first glance, it's like, okay, L is the same, G is the same. But I don't know how the acceleration would affect the period, right? Because our two main variables that do affect the period remain the same. The way that I kind of thought about this, and maybe you might have thought about it differently, you got to look at your frame of reference. So if we're just, let's say we're watching this watching this unfold within our eyes, or yeah, we're watching this all unfold. We have we're on the ground and we're not accelerating either, and we're looking at this box and we're looking at the elevator, right? That would be an inertial frame of reference. We're in the same frame of reference as the box pendulum. I'll call it that, box and then elevator. If we're in the same frame of reference as the box, and we would measure L and we would measure G, kind of the same, right? We both experience the same G, that sort of thing. But when you're in the elevator's frame of reference, right? If you're standing here, right? What would the pendulum be like for you? I guess what I'm getting at is, if I was standing on Earth with the box not accelerating, I would draw my FBD for the box pendulum like so, right? I would draw an FT, the tension keeping it still, and this is before I get it swinging. FT to keep it still, and the weight of the pendulum dragging it down, and those forces are equal because not accelerating. And if I was in the elevator situation, I would have the same FG pulling down. You can say it's the same pendulum, but there would be a greater FT causing that acceleration. And I would even go as far to say as FT minus, so I'll say like this, FT minus minus FG equals MA, the acceleration, right? Of that pendulum, because the elevator and pendulum accelerate at the same rate, so they both share the same acceleration. That's all fine and dandy, but what's gonna happen for the guy in the elevator? So let's say this is box person's FBD. So box person's FBD. What about the guy in the elevator? How will his FBD look for the pendulum? Well, he's going to be like, okay, the weight of the pendulum, I'm going to say, is like so. FG. Or I don't know why I drew it like, I don't know why I erased it. I was like a perfectly good FG. FG, or no, I know why I erased it. Okay, FG, like so. And let's say he calls box person and he's like, what do you think the tension is? And let's even say this, like elevator person knows that the elevator's accelerating up relative to the relative to the observer or the box person, right? It's accelerating up. So, he paid attention in physics class. He's like, hey, tension has to be bigger, right? When in the back of his head, he's thinking, wait, how can the tension be bigger than the weight of the than the weight of the pendulum if in my reference frame it's not accelerating, right? Like how that's kind of contradictory, right? For the box person, Ft has to be greater than Fg because it's accelerating up. But for the elevator person, Ft has to be the same as Fg because it's not accelerating, right? That's just Newton's second law for you. The truth is, here's the thing elevator person doesn't know. Newton's second law kind of only holds for an inertial frame of reference. When you have a non-inertial frame of reference, when when your frame of reference is accelerating, right? Newton's second law doesn't really hold in the same way that it would for an observer who is in an inertial frame of reference. What has to go on, or what's going on, is in this non-inertial frame of reference, there's really a fictitious force. There is some fictitious force that is present that allows Newton's second law to hold in that non-inertial frame of reference. And then so if I were to do Ft, so we'll say this is box person, and then for elevator person, your FBD would be like so: Ft minus Fg minus that fictitious force. It's going to equal 0 newtons, right? So, like, there's that fictitious force. Awesome. Now, here's what's kind of cool. What you could kind of say is that, okay, if we needed, let's go back to box person, right? He's like, okay, sure, this elevator guy thinks there's a fictitious force. If we had a fictitious force, that fictitious force would need to be large enough to basically make the acceleration 0, right? Like that, like it has to be large enough of a force to balance out the tension, and help the Fg balance out the tension, I should say, right? So whatever that fictitious force is, it needs to be a certain size. That size would need to make the left-hand side of this equation 0 so that there's no net force. Well, how do you do that? Well, you subtract each side by ma. So I get that. So what I get here is Ft minus Fg minus ma would have to equal 0. In other words, if a fictitious force, if a force needs to be added that would make the net force 0, it would have to have the size of ma, right? It would need that size, mass times acceleration. That's how many newtons of force, right? So if this pendulum is 2 kilograms accelerating 3 meters per second squared, that fictitious force would need to be 6 newtons in size. So this, I'm not saying this is the fictitious force, but in size, in quantity, it is equal to the fictitious force. So this can really serve as our F fictitious, and we could say that Ft is really equal to Fg plus ma, which is really equal to mg plus ma, which is really, equal to, if you factor out the m, g plus a. So another way to really look at this is in this elevator, in this non-inertial frame of reference, because the pendulum is balanced, this is before it starts swinging. Before it starts swinging, right? Like the gravitational field strength is essentially G plus A. In this elevator, it's like the pendulum is a little bit heavier in that elevator, right? When you're observing with that non-inertial frame of reference, the pendulum appears heavier than it actually is, and that's kind of what happens in an elevator, right? You feel heavier, your apparent weight is larger. So the gravitational field strength is a little bit more than g, it's going to be g plus a. Like the apparent gravitational field strength. Hence, in an elevator, the period becomes 2 pi square root L over g plus a. So it's going to be a little bit larger. Thank you for watching. Hopefully this made at least a little bit of sense. I sure hope so. Am I right?